All right, guys, so today we're going to look at something that is known as the structural idealization. So it's basically something that we have been using a lot in this class, but this is something that Johnny had covered in Structures 1. But since I think we have time, I think it's important maybe to go back and make sure that you know how to do this, okay? All right, so what we learned so far is that aircraft structures are assumed to behave as something that we define as thin structures which implies what? So aircraft structures are assumed to behave as thin structures, implying that bending stresses are of most importance. So basically, what does that mean? What was the expression for, the simple expression for bending stresses? We had sigma equal to what? My over I, okay? So over here, what do we know? We know that sigma is the stresses, m is the bending moment. So this one is related to what? This is related to the loading. Okay, and then this is the important part here. What is I? I is the second moment or moment of inertia, or the moment of inertia. And this one is related to what? This one is related to the cross section, okay? That's why when we did the finite element and went to the beam element, which is a 1D element, do you remember we were able to select different cross sections? Because depending on the cross section, you will have different I, no? Okay? And Y, if you want, is part of the geometry, okay? So, and Y is really what? Distance to neutral axis. All right? So if you needed to do a simplification of an aerospace structure, if you needed to do the basic modeling in one of these parameters, M, Y, or I, which one would you pick? M is part of the loading, so there's not much you can do, no? Okay? If the structure has a certain height, that's not something you want to change, no? The depth of the structure. So what is something you can do? What is important is that you try to model what would be the I, which is the resistance to bending, no? So maybe if you needed to base your idealization on something, the best parameter would be to select the second moment of inertia. Okay? So over here, let's plot that. All right, so the most important parameter to consider for the idealization is the moment of inertia. Okay, and all this comes because we make the assumption of thin structures. Okay, if it's thin, that means that the structure is going to break in what? In shear or bending? It will break in bending, no? Okay, and this expression here is for bending stress. I is the resistance of the structure to bend about a certain axis. Okay, so I should be the most critical factor that you want to be able to keep during the idealization. Okay. Okay, so we have two different types of members. We have vertical members and horizontal members. So let's see what will happen for a vertical member. So let's do here vertical members. So this could be whatever you want, a flange, a stiffener, okay, etc. So over here, what are we trying to do? We have a say this is our real member, okay? Our real structural member. And we want to idealize this one. Okay, you can go back and forth. And all the structures we have been studying now, how do they look like? You will have some type of area over here, some type of area over here, and these ones are connected, no? Okay, so the whole thing is that how do you go from this one to this one or vice versa? How could you go from this one to that one? So let's say over here that the height of our vertical member is h. So obviously that's something that we want to keep in our idealized member. We want to keep the h, okay? And now let's call here the width of the member B. And let's call these areas here A prime, okay? So if you want, here we have the real member. And this will be the idealized member. Okay, so keep that figure. I need to go to another page. Let's keep that figure over here. All right, so if you can see the figure over here, let's first do what would be, oh, maybe one thing is important. So for each one of them, if this is symmetric, the neutral axis should be at the same location, okay? Okay, and here, let's just say that our reference frame is going to be of this form over here. Y and X, okay? I take this reference frame, okay? So for the real member over here, what would be the moment of inertia of this vertical member? Will be the base, so 112, times the base times the height cube, okay? And I don't have to do this because I don't want to do too many of these ones. They are too big, started to do them too big. Okay, and this now should be equivalent to the idealize. So the idealize should be what? Let's call this one I prime XX. So this is about the neutral axis, okay? This is the moment of inertia about the neutral axis. So it's about the neutral axis. So this one, the moment of inertia of the two areas over here, generally they will be assumed to be zero. So this will be equal to the moment of inertia, if you want, of the I xi. Here I is 1 to 2. So this is moment of inertia of these two spheres really will be about the neutral axis is 0, okay? But now, these two areas A prime, they are not centered by the neutral axis. So we need to use the parallel axis theorem to move them from here to here, no? Okay? So that would be what? Plus A prime, leave a space up front. At least I'm going to leave it because I'm not going to have space. Times, how far are they from the neutral axis? They will be at a distance of h over 2 squared. I hope you remember the parallel axis theorem. We use it already, no? And here, how many do we have? We have 2, one on top and one at the bottom. So it will be 2 for top and bottom, okay? Top plus bottom. Okay, so what do we need to have? We need to have these two to be equal to this one, no? So this will mean what? That we need to have 112 b h cubed needs to be equal to 2 times a prime h squared over 4. Okay? So if we solve this, well, what are we going to have? We're going to have, so it will be 1/3, no? Over here. So, oh no, because it's just 2. No, okay, so 4. So we have, so it will be 1/2. So it will be 1/6. Multiplied by 2. Okay, I mean, let me rewrite this. I think I'm correct, but b, if we eliminate the h first, we can cancel this one. Then we'll cancel with 2 of this. So this will mean we have 1/12 of bh equal to a prime over 2. Okay, that's what I was trying to say before. So this will give you that a prime is equal to 1/6 b times h. Okay, and what is b times h? Maybe we can go and put it in this figure here. All right, let's say that a here, let's go to a different color. So for the real member, we have a of this member would be what? B times H, no? Okay. So here we have A equal B times H. So basically, this will give you that the idealized structure, the A prime, should be equal to 1/6 of the area of the original structure. Okay? So it will be A over 6. Okay, where A prime will be the area of this idealization over here. Okay, so now we're going to do exactly the same thing, follow exactly the same procedure, but if we did a vertical member, next thing we need to do is horizontal members, no? So vertical, horizontal members. And again, this could be flanges, stiffeners, and so on. Stiffeners, I'm going to put etc., but you could also have webs and so on. So this time, be careful here because this might be a little bit different if the cross section is not symmetric. So let's say this will be the top member, okay? Keep in your head, let's say you have a structure which is this way, okay? Yeah, this would be the simple structure, no? So on this one, we did the vertical members, which basically are within the neutral axis. But now these ones will be on top and the bottom of the neutral axis, no? So we can say that, let's say the neutral axis will be somewhere over here. And this time, let's do the dimensions. This will be I'm going to change the notation to what I have here. I'm going to call this L. That way we don't have too many of these ones. L. Now I need to be careful. I'm going to call this, we can call it B as well. That one we can call D. All right. And let's say that the total depth of this one here, so let's call that distance here to use the same notation as the other one, this will be H over 2. Do you understand the figure? Because that's the important part, okay? Oops. Okay, so I did too big the figure. So I'm gonna have to go to the next page and redo it, but it's fine. Okay, so I'm gonna go to the next page and basically just redo it. All right, so let me redo it here very quick. L B neutral axis, and we say that distance here will be H over 2. So this will be, how do we call it on the previous figure? This will be like the real member. And we need to do the idealization. So how will be our idealization? Will be again this one over here, where we want to keep the distance L in between. And this one, using the same notation as before, this will be a prime. And again, this will be at a distance h/2 from the neutral axis. So this will be our idealized member. Okay, so over here, what will be the IXX of our real member? So now remember, we look at this one is not centered anymore about the neutral axis, no? So we need to calculate about what would be the CG of this one. That would be what, 112? What would be the base? L times B cubed, okay? But now we need to move this one, which will be our A, where A is equal to what? Is B times H, no? Will be A times D squared, which is H/2 squared. Okay? So one thing before I do the other one. So for thin structures, okay, so thin structures, the assumption is what? Is that L is much, much bigger than the thickness of the element, no? Okay? So if L is very big and B, let's say, is very small, let's say it's 0.1 inch. If you do 0.1 inch to the cube, it's going to be a very small value, no? So let's say that we can neglect the first term over here because of the thin structure assumption, okay? Because B is very small compared to L. So this member will become insignificant compared to this one. All right. So we do the same thing as before. Now, what would be the I prime XX for the idealized structure? So same as before, let's see what notation I use, would be the summations of the two. Well, you have to use I prime, it doesn't matter, just don't use I prime, but the moment of inertia of the two masses, circular masses, is assumed to be 0. And now what do? We have two of them. We have two A prime. And how far are they from the neutral axis? To a distance of H/2 squared. So basically this term is identical to the one before. Okay? No changes. So now, if we solve over here, these two needs to be equal to each other. So we're going to have A of H/2 squared needs to be equal to what? To A prime of h over 2 squared. So over here you see right away that these terms will cancel out, which will give you that the surface of the idealized structure needs to be half of the area of the real member. Okay? Okay? So let's do an example. So example, so let's say that you have the following real structure. Okay, and let's say here would be like a little reinforcement. Way. Okay, so let's say you have some stiffeners at the edges to reinforce your structure, okay? And we know about this structure that it has a depth of the structure is 8 inches. This length of the structure is 48 inches. Okay, the thickness of all the members is T, and T is equal to 0.05 inches. And now imagine this one has an area A1, A2, A3, A4, okay? So that this will be points 1, 2, 3, 4. So in this example, we're going to need to find two things. So determine A, the idealization of the aircraft structure and B determine the direct stress at point 1 for the moments mx equal to 500,000 pounds per inch and my equal to 100,000 pounds per inch. Okay, so we need the structure over here. So part A, idealization. So obviously when you idealize, you're also going to simplify because, as I told you before, if you simplify structure, it's always safe because you will have less members to support the loading, no? Okay, so if you remove members and if it's safe, it will be safe if there is more area or more members to resist the external loading. Okay, so let's do a very simple idealization for this structure here. The idealization will be just to have this here, another one here. Oh, and another one here. Let's go back to the first figure because I forgot to give you some data here. So in this figure over here, you can put it where the T is, or right at the bottom. We know that the area 1, so of this stiffness here, equal A2, and that is equal to 0.5 inches square, and the two at the bottoms, A3 and A4, are also equal, but to make things interesting, I'm not going to make them equal to 0.5, but to 0.75 inch square. Okay? So that's the A of this difference. So what we need to find in this figure will be what? We need to find here the A prime 1, A prime 2, A prime 3, A prime 4 are unknown. And we still know the length will be L. And the depth or the thickness of the whole structure will be H. Okay, so using what we just derived before, what is the equivalent area for a horizontal member, and what is so this is for a vertical member, and what is the one for a horizontal member, which is A over 2 and A over 6, no? So using these two relations, here what do we have? At A prime 1, we're gonna have what? The area of this one, A1, no? Plus the area of the vertical, plus the area of the horizontal, no? That's basically what we need to do. So that's what I'm gonna write down. So areas of the idealized structure are the sum of what? So we just say here, one will be area of, let's say, stiffener. So in this case, if we look at the figure, what would that be? If we do A prime 1, will be A1, no? Okay, so it will be A1 plus the area of the vertical members. So that would be what? 1/6 area of adjacent vertical member and 1/2 area of adjacent horizontal member. So this is pretty simple. So basically, if we do A prime 1, A prime 1 will be equal to what? If we don't look at the idealized, will be equal to A1. The little area over here, so will be equal to A1 plus what? 1/6 of the area of the vertical member. So that will be 1/6. What is the area of this vertical member? The one over here will be 8 times T, which is 0.005, no? Yeah, so if you want, let's try to do it symbolic. So will be, let's see, will be 1/8, so let's say of H times T, and maybe let me put T over here on the drawing, of H times T. So it will be half of that area, because that's what we evaluated before, plus what? Now we need to look at the horizontal member. And that will be just half plus 1/2 of the area of this member. That would be equal to what? L times T. Okay? So if we put numbers to this, what do we have for A1? A1 was equal to 0.5 plus 1/6 times 8 is 8. T is 0.05 plus 1/2 of 48 inches times 0.05. And if we do this calculation, we find that A prime 1 is equal to 1.767 inch square. Okay, so I'm going to write it down, but what should be the value of A prime 2? This member is the same as this one, no? And this one is the same, no? So really A prime 2 should be equal to A prime 1, no? Okay, but let's still write down the equation. So we'll have over here, I don't want to break this page. So we can write down similarly. You will have what? A prime 2 will be equal to A2, so it would be exactly the same expression plus 1/6 H times T plus 1/2 L times T. Okay, so in other words, we're gonna have here A prime 2 will be equal to A prime 1, which is equal to 1.767 inch square. Okay, so now we need to be, it would be kind of the same again. What would be A prime 3? A prime 3 should be equal to what? A3. What is the vertical member? Plus 1/6. So all the rest is the same. HT plus 1/2 LT. But this time, what is A3? A3 was equal to 0.75 inches squared. So it's the same as before. You just need to add 0.25. So it's 0.75 plus 1/6 times 8 times 0.05 plus 1/2 times 48 times 0.05, and this will give you an idealized area F prime 3 equal to 2.017. Okay, it will be really 2.0167, but let's just round it off. Okay, and obviously A prime 4, since these two are the same, will be the same, but let's write it down. So A prime 4 will be equal to A4 plus 1/6 plus 1/2 H times T plus L times T. And here we're going to know that A prime 4 equal to A prime 3 equal to 2.0117. So that really our idealized structure is where this will be A prime 1, A prime 2, A prime 3, and A prime 4. Okay, so In this problem, where will be the location of the neutral axis if A prime 1, A prime 2, A prime 3, A prime 4 were equal? It will be right in the middle, okay? But in this case, we know that A prime 3 and A prime 4 are bigger than A prime 1 and A prime 2, no? So this will mean that the neutral axis is not going to be in the center, but should be a little bit closer to A prime 3 and A prime 4, no? Okay? So if we kind of plot it a certain way, probably I bold it completely, okay? We know the neutral axis should be somewhere over there, okay? So in other words, the neutral axis is going to go through the centroid. So again, this is statics. No, this is more solid, okay? How do you find the location of the of the center of gravity? So, what is the definition? What is the physical meaning of the center of gravity? When you take a pen or something, okay? Janli, how do you find the center of gravity with your fingers? Is the point where not that much balances, but it's the point of zero rotation. Is it here? No, because it rotates, no? When you take it all the time, it's always a point where there is no rotation. Okay, if you want to, you call it an equilibrium, but it's rotational equilibrium, no? Okay, so the way to write that down is that the moment created by these four areas, correct, needs to be balanced, no? So the moments created by A prime 1, A prime 2, about a certain line needs to be equal to the moment created by A prime 3 and A prime 4. Okay, does that make sense? That's what is the neutral axis, okay? So over here, to simplify the calculations, it's just to, you could really take the origin of your reference frame anywhere you want, but let's select this one here. So let's say this will be X and Y, okay? That way we eliminate some values. We just said this will be the origin of our reference frame. If we put it here, we do that all the time for the moments. What we do, the moments created by A prime 1 and A prime 2 will be 0, no? Only A prime 3 and A prime 4 will be created in a moment. All right, so obviously the most important part is to find what is the Y location of the neutral axis. So the equation is Y. So really the equation will be that the location of the neutral axis from this point created by all the masses, okay, moment, no? That distance, that's all the masses, needs to be equal to what? To the summation of the distance to each one of the masses times each mass. This is the definition really of centroid, okay? So from here, you know that the location of the centroid, Y bar, is equal to what? To the moment created by each one of those areas divided by the area of all the different areas. So over here, because we selected the X and Y to have the origin over A prime 1 and A prime 2, that will mean, like I said before, the moment created by A prime 1, A prime 2 will be 0, okay? What will be the moment created by A prime 4 and A prime 3? So what would be the arm? What would be the Y? The Y will be that distance here. If I remember right, we had 8, no? So this was H was equal to 8 inches. Okay. So I'm going to put numbers. I think it's going to be a little bit faster. So what is the location of this one? Will be the y is -8 times, let's do first a prime 3. So let me put here, maybe I write over here. This will be y of 3, a of 3, plus y of 4, y of 4, divided by, oops, it's a primes here, but the a prime, sorry. I want to be accurate, a prime 1, a prime 2, a prime 3, a prime 4. Okay, a prime 1, a prime 2 is 0 because they go through the axis, no? Okay, so you want to put it here. Okay, I don't want to put too much information. So this will be -8. What is a prime 3? Was equal to 2.017 plus -8 times 2.017. And we need to divide that by the area of a prime 1, that is 1.767 plus 1.767 plus 2.017 plus 2.017. And this is going to give you that the location of the centroid, which in this case will be the neutral axis, is at -4.26 inches. So if you come to the figure, what does that mean? What is that distance? That's the distance over here, which is 4.26. No, this will be the y bar. Okay. Okay. Since this is symmetric, where will be the location of the x? Should be in the middle, no? I don't think we need to do the equation to show that's in the middle. I mean, if you want, we can do it, but I don't think it's not needed, okay? All right, so I think for part A, we can stop over here. Let me do a little pause in case you have a question. But I need to be able to get this stuff on top to pause the video, which I'm never able to get it. Oh, there we go. Okay, so now let's do part B, which is to determine the bending stress or the direct stress at point 1. Okay, so again, I'm going to redo a figure. Okay, well, this is the neutral axis. And we say this is at y bar was equal to 4.26. Okay, so from the problem statement, we know that mx. So loads is loads. We know that mx is equal to, it was, okay, 500,000 pound-inches, and that my is equal to 100,000 pound-inches. And we know our reference frame is basically y and x, okay? Okay, so here, let's be a little bit careful because I don't like to write these equations by memory. I mean, the sign, obviously the equations by memory, but the sign. So if this is going counterclockwise, what should be the moment? Should be going, so should be coming out, so should be, mx should be bending so what will we have over here? We'll have mx will be bending, I mean, I don't have to show, I cannot show it on the screen, but it will be bending this way, no? So in other words, due to the mx positive, 1, 2 will be tension or compression? If it's bending down, with this one being tension or compression? Okay, so let me write down the equation. So sigma on the z will be equal to mx times the distance y, which would be that distance here, times y. And what is the axis resisting the bending in that direction? Will be the ixx. So this moment we create the 1 and 2 will be what? Tension or compression? 1 and 2 will be in compression, no? Okay, so let's say here, stress at 1. So if it's compression, that means that it needs to be negative, no? And the y is positive, so I'm going to put a minus sign over here because it will be compression. Now, the moment my is going to create bending about which axis? About the IYY, so will be, let's forget about the sign for now, my. And now we need to pay attention to what? The distance between the axis of rotation and the point we want to calculate, no? That will be x. And what will be resisting the bending in direction will be the IYY. So if the moment is positive in that direction, it means that my will be going this way. Where this time down will be in tension, I think, okay? This one would be in tension, all right? Think about when you bend this way, you bend this way or this way, no? Okay, that's what you need to look at. And this one will be bonded up or down. So if it's bending in this form, this side will be in tension, this side will be in compression. Okay, so we know mx. So in this equation, we know mx is given. What would be y? Is that distance here, no, from the neutral axis, 2.1 is 4.26. And what will be x? Half of the length. So it should be here 24. Or here should be actually minus 24. So we'll have minus 24. Oh, so that's, okay, I think here when I put 24, I already took that into consideration. So just put the magnitude, 24. Okay, so we need to find Ixx and Iyy. Okay, so again, the Ixx will be equal to the same thing as before, which is the summation of the moment of inertia of those little circles plus the one of the areas, the distance squared. And we know this one will be 0 because the moment of inertia of a circular part is 0. So we have the figure over here. All right, let's do the first one in detail. What is the area of A1? 1.767. What is the distance D? Here will be the Y bar, so which is 4.26 squared, no? So basically this is equal at the end, A1 D1 squared plus, so A prime 1, sorry, plus A prime 2 D2 squared plus A prime 3 D3 squared plus A prime 4 D4 squared. So basically we have here the same thing again because A2 has the same area, so 1.767 times 4.26 squared plus now A3, which the area is 2.017. Okay, so here I need to do an extra calculation. What would be that distance over here? If this is 8 minus 4.26, that will be 3.74, no? Inches. So what do we need to put over here? This one will be at a distance of 3.74 square plus 2.017 times 3.74 square. And this is going to give you a value of Ixx equal to 120.8 inch to the 4th. Okay, similarly, Iyy will be equal to the summations of the little circles that will be 0 plus this time the summations of the A prime I times di if you want square, but this, be careful here because this time the d should be, so if you want, this will be the dy's, no, the di's doesn't matter. I want to change too much. So this will be equal to what? This will be equal to A prime 1 x1 square plus A prime 2 x2 square plus A prime 3 x3 square plus A prime 4 x4 square. Here maybe I should have replaced the d by y's, but too late. So this one is very simple. What is A1? 1.767. What will be the distance between 1 and the neutral axis? It will be 24, no? Half of 48, so it will be 24. Maybe let me put it on the figure here. This is 24. 24, okay? So again, plus 1.767 times 24 plus 2.017 times 24 plus 2.017 times 24. And this is going to give us an IYY equal to 4,359 inch to the 4. Okay, so finally, the direct stress at point 1 is, and I'm going to rethink about it because let's see if I can do this correct. So let's just relook at the expression we had before, sigma z at 1. What is the expression we had? Okay, let me rethink about it. mxy, ixx. Don't put any sign because we're going to discuss it again, and iyy. So this will be equal to mx. We had to be equal to 500,000 times y. What is y at that location? For 1 is 4.26. And this will be divided by the ixx that we just calculated of 120.8 plus my, which is 100,000 times 24 divided by 4,359. Okay, so let's rethink this stuff over here. So I look at the two equations. So let's look at the cross section. So if the moment here is positive, that means that this is going to bend this way, no? So it means the top will be in compression. So if in compression, this should be negative. So this term will be here in compression. So it should be negative. Now, if this is bending this way, so this will be bending this way. So now 1 will be in tension. So I think it's what we had before, no? So plus, so if you want, this side will be, this term will be in compression. and this term will be in tension. So if you do the calculations, this will give you that the direct stress at 1, so I think you get a negative value of 171,000 pound per inch square, which is really, you never write on this form. In structure, you call this PSI, no? Okay, so I will terminate the video over here. Now it's not going to take me long because I learned something today. And stop recording.